Progress. Okay, so we're gonna finish talking about moments and centers of mass, and then we're gonna talk about our last topic for this chapter. So let's do this. Okay, let's go to writing mode. My window capture is not right. There we go. Cool. Let me spotlight myself. There we go. Yes. Okay. So last time we talked about moments and centers of mass, and we found out that the moment is just the mass times the distance from the balance point. Interestingly enough, so one of the things that we talked about was that this center of gravity, that formula is the same as what? So like we had the formula like, oops. Okay, why is it not letting me click? WTF, what the hell's going on with my screen? What the Okay, there's like something wrong with my thing. What is going on? Okay, one second. I'm like having technical difficulties. What the hell? Okay, I can draw with my mouse, but it's not letting me. Oh, there. Okay, something is like. What the hell? Okay, something is like going weird with my thing. Yeah, what the hell? Okay, I think I'm just gonna have to unplug my little writing tablet and like I'm like trying to write with it and this is not working, so I'm like, what the hell is going on? Okay, come on. Maybe I need to reconnect it as Bluetooth. Thank you for your patience. I'm like not sure why this isn't working. Okay, I'm trying. Okay. There we go. Oh my god. Okay, I was like about to lose my shit, to be honest. I was like, what the hell is going on? Okay. Woo! Okay, restart. We talked about centers of gravity, and there's these things called moments, which are the distance from your point mass to the center of gravity. And we have a formula to find the center of gravity. You can see it right here. What is this formula very similar to? Oops, why does it keep doing that? So I've said that this formula is similar to something. This one right here. Where you like add up all the things and you divide by the total mass. Like this formula is, yeah, it's actually similar to the mean. And if you were to take a calculus-based statistics course, you would find out that there's something called the moment of a function, which is related to what we're doing here. So like this section is actually really important for understanding like more advanced statistics if you're ever interested in learning that. So like it's just like a shout out to like how this information is cool and what you can use it for someday. Okay, so we did some examples where like we calculated like where would you balance these masses, the four masses, right? Like, you know, 30 kilograms, 5 kilograms, 10 kilograms, 15 kilograms at like different places on your seesaw. Where would you put your seesaw? Okay, and then we went and we did an example eventually with if you work in 2 dimensions, right? So like now you can place your 3 masses somewhere on a plane. All right, so in the example that we did, we had like 3 masses, one with 2 kilograms, one with 4 kilograms, and one with 6 kilograms, and we placed them at these different places, and we calculated that. And it was actually pretty easy to do because you just calculate the x coordinate using the same formula, and you calculate the y coordinate using the same formula, right? So you do the moments divided by the total mass, right? So this is the x moment, and this is the y moment, right? The moment, remember, is the mass times the x coordinate for the x moment, or the mass times the y coordinate for the y moment. Okay, so we went and we did that. And then we started talking about, what if your density wasn't constant or you had some sort of weird shape? Okay, so here we had this shape, we call them a lamina, right? It's like you can imagine it's like a sheet of metal that's been cut in this like weird thing. It says 3 straight sides and then a fourth curved side on top. Okay, there we go. So we're wondering, like, well, where the hell is the center of gravity of this thing? Okay, so we have some terminology for this. We talked about how the geometric center is called the centroid, and if your density is constant, your center of mass will be at that centroid. So now we're wondering, like, well, how do you calculate this thing? Well, it comes back down to the formula we learned about. And we're gonna, like, redo this today. Okay, so like everything that we've done, we started off, we had our lamina right here. Oops. Okay, sometimes I just feel like the technology hates me. I mean, I know it doesn't, like, actually give a shit about me, but sometimes I'm always like, why is this happening? So here is our lamina. Okay. And like everything we've been doing with integrals, we decided to break it up into 4 representative pieces with rectangles, right? So we have our x0, our x1, our x2, our x3, and our x4. They split up from A to B into the 4 parts. We always just draw it with 4. And we draw our 4 rectangles, and then we decide to look at one of these rectangles right here. We're looking at this one. Okay. So, oh my god, burrito. He's a hater. Shh. Stop. He's angry. Okay, I'm just going to redo these calculations. Okay, so you have this rectangle right here. Let's draw it. I'm going to draw it off on the side. Okay, and we know that this rectangle is delta x wide, and in this case, this was the x1 value, and this was the x2 value, right, on the left and the right. Okay, so how would you calculate the mass of this thing? Well, the mass is going to be the area times the density, right? And if you look at this thing, the mass, let's call it mi, your mass is approximately equal to, well, the area is going to be the width, which is delta x, times the height. And then we talked about this last time. We usually choose this point x star, which is the midpoint, right? So we'll take the height at the midpoint, and that's going to be pretty good to estimate the area. And then you multiply that by rho. Okay, so looking at this, remember how the formula for the moment, I'm sorry, the formula for the center of gravity is equal to the moment divided by the total mass. Okay, so your total mass is just going to be the sum of all of those masses. Delta x times f of x star times rho. Okay. Now we need to calculate the different moments, and there's 2 different moments. There's the x moment and there's the y moment. So the x moments, we have our formula. We have the y moments, there's a formula. So the x moment is going to be the mass of your object times the x value. The y moment is going to be the mass of your object times the y value. Okay, so now we need to calculate these for this thing. Okay, so if we're talking about the x moment, you're measuring how far your center of gravity is to the x-axis. So I'm gonna just draw it, and remember the x-axis is right here at the bottom. And then over here will be your y-axis. Okay, the y moment is going to tell you how far that point is from the y-axis. So it's going to be that value. Okay, so if you're looking at this little box right here, the mass is going to be rho times f of x star times delta x, that's your mass. And then the value to the x-axis is going to be, we talked about this last time, f of x star over 2, right? Because remember the height of this rectangle is f of x star, and that point right here, how far is it from the x-axis? Half of that y value. Okay, now the same thing happens for the y moment. You have your mass, which is going to be rho times f of x star times delta x. Now, the y value is how far that this point right here is from the y-axis. So what is this distance right here that I'm talking about? How far is that point from the y-axis? So how far is that? Like the point of the height of that point was f of x star. What's the distance of this point over to the y-axis? And this is where I find out if people are able to follow me or not. So I'm going to pause. How far is that point? Yeah, it's x star, good. Which actually now gives you your formulas, because to find the actual answer, you're just going to take the limit. You're just going to take the limit of these sums. Oh, I'm sorry, I forgot to put the formulas here. Okay, so when you take the limit of these things, you're going to get that your x moment is the integral from a to b of rho f of x, I'm sorry, yeah, rho f of x, f of x squared over 2 dx. All I'm doing is taking this formula and simplifying it. And then your y moment, oh, and then all this is divided by your total mass. And then your y moment is going to be integral a to b rho f of x x dx. And I got that by looking at this one right here. Boom. So if you want to find the center of gravity of some shape, that's what you need to integrate, basically. Okay, and understanding it goes back to this little thing we drew right there. Oof, that was a lot. How's everyone doing today? I'm going to pause. Are we following, not following? Where are our minds? I'm going to allow people to write stuff down, see if there are questions. Wait for a response. And I'm also just rejiggering stuff on my desk. Okay, good. I need to move my book so I can read it. I sort of hate this book. It's huge. And I have nowhere to put it on my desk. So I'm trying to look at it, but it's in the freaking way. Navigating a migraine? Oh, I'm sorry to hear that. That's hard. this like junk has appeared on my screen. There we go. So why do you square f of x in the mx? Because when you look at the x one, which is this one, okay, you have your mass, which has a rho, an f of x, and a delta x. And then you need to measure that distance from your point right here to the x-axis. In other words, this. That is a height of f of x divided by 2. So you get 2 f of x's, one from calculating the mass and then one from your distance to the x-axis. So when you put them together in the formula, you get f of x quantity squared. So it's like the fact that you get 2 f of x's. And then where do you get them from? One of the f of x's comes from the blue in the calculation of the mass. The other one comes from its distance to the x-axis. Because remember, this is a moment that we're calculating. A moment is the mass times the distance to your center. There's a 3 f of x in my... no. It should be rho... Oh, I see it. Like, my bad. Okay, I see where I made a mistake here. Sorry. This part, right? Okay, so what do you get in there? You get a rho. There's an f of x quantity squared, and then it's divided by 2 dx. I had an extra f of x there. There should only be 2. One from right here, one from right here. I don't know why. I don't know why I had it written like the way I did before. There was like a copying error on my part. So the other one is correct. Yeah, your rho, your f of x, your x, and your dx. The one over here. Okay. So let's use this to calculate something. Example. Find the center of gravity, or center of mass, for the region. Okay, so let's draw the region. So let's say, oops, why does it keep doing this? Okay, so let's say the region you want is f of x equals square root x. And we're going to go from x equals 0 to x equals 4. Okay, so you want this region here. Okay, so we want to find the center of mass for this thing. So you can imagine you have this like little plate, right? Like it's cut, it has these 2 straight sides, and then you have that thing like that. Okay, so basically you're looking for the x and y coordinates of like, where would you put a balance so that this would balance properly? Okay, so you're going to have to calculate them separately. Let's find the x one first. So what is your x moment? Okay, so we're going to need to integrate from 0 to 4. Okay, and then rho is our density. Let's just let the density be 1, because it doesn't make any difference. Okay, and then you're going to have your f of x, which is root x, and you're going to square it. You're going to divide that by 2 dx. Okay, and then you're going to need to divide that by the mass. Okay. So we're going to solve that one. So let's solve with the masses. So remember that the way that you find the mass is that you integrate rho f of x from a to b. right? Because remember the mass, the total mass is equal to the sum of all the different masses. And the way you find the mass is you do the density times your function. So you're going to integrate that from 0 to 4. Let's just let rho be 1, and f of x is root x. Lotus, can you stop scraping? Okay, so what's our antiderivative of this? Okay, so we have x to the 1/2. Okay, so you're going to get x to the 3/2 times 2/3. Okay, so when you calculate your f of 4 minus f of 0, the f of 0 is not going to affect anything. So what's your f of 4? You're going to get 2/3, 4 to the 3/2. Okay, so 4 to the third is going to be 4 times 4 is 16. 16 times 4 is 64. The square root of 64 is 8. Okay, so that's going to give us 16/3. Okay, so you've got your mass. Okay, why do we need that? Because when we go back up here to calculate the x moment, we're going to need that number. Okay, so when I calculate my x moment, this m is going to be replaced with 16/3. Dividing by 16/3 is going to be the same thing as multiplying by 3/16. So I'm going to have 3/16 of the integral from 0 to 4 of the square root of x squared is just x. And I guess I can factor out that 2. So if I factor out the 2, you're going to get a 32 right here. Just put a different color. We're going to put 16 times 2. So you can see where it came from. Okay, then when we integrate that, that's not that bad. The antiderivative of x is going to be 1/2 x squared. So you're going to get 3 over 32 f of 4 minus f of 0. The f of 0 is not going to affect anything. So you get 3 over 32, and then f of 4 is 1/2 4 squared. 4 squared is 16. 16 over 2 is 8. So you get 3 over 32 times 8. And then what's 8 divided by 32? It's going to be 4, so you're going to get 3/4. Okay, I think I might have made a mistake somewhere. It's fitting on my desk. Sorry. 1 second. And I clicked away for there it is. I think I made a mistake somewhere. Oh, that's fine. Yeah, so I get 3/4. Okay, so what does that mean, practically speaking? It means that my center of my... Yeah, we calculated mx, yes. Did I put this for the right one? Yeah, that's mx, yeah, because we had the f of x squared. So according to this, where's the x coordinate for my thing going to be at 3/4? So somewhere here. That just doesn't seem right to me. So I'm looking at this number and I'm freaking out that something is wrong. It doesn't seem to me when I go and I look at this that the center of mass should have an x value right there. So I'm wondering what is going on. I made a mistake somewhere. Does everyone get what I'm saying? If you look at this piece of metal, you would not want to put your center of gravity on that line right there. Does that make sense though? Like why I'm like mistrusting what I'm writing here? I'm like looking at this and I'm like, this is no bueno. Well, how did I get the f of x for... Oh, because if you look, that what you have to calculate is you're going to take f of x quantity squared, right? The square root of x squared is x, and the antiderivative of x is 1/2 x squared. So that's where that came from. But like this number, like it doesn't seem like that should be the right answer. Like if you look at it, 3/4, that you wouldn't want to balance that on that. So I made a mistake somewhere. So give me a moment trying to figure out where I went wrong. No, because you're dividing by m. M is 16/3. So if you're dividing by 16/3, that's the same as multiplying by 3/16. Yeah, so that's not the problem. Oh, shoot. I found what the problem is. Okay. No wonder. Okay, I found it. This is the problem. Oops. If you want the x coordinate of your center of mass, it's the y moment over m. But if you want the y coordinate of your center of mass, it's the x moment over m. And which one am I calculating here? I'm calculating the x moment, which means that is going to be you're going to use that to determine the y coordinate of your center of mass. Okay, so it's not that I made a mistake, I'm just using the number for the wrong thing. Okay, so I have my square root x, there we go. Oops. I'm trying to draw this, sorry. Okay, so what this is telling you is that y... Why is it doing this to me? Y equals 3/4. So your center of gravity is going to be somewhere on this line. There we go. I was drawing the wrong line. It totally makes sense that your center of gravity could be like right here somewhere, right? So this is okay so far. Okay, so you calculate the x moment to figure out the y coordinate. There we go. Okay, so now we need to calculate the y moment to figure out the x coordinate. So the x coordinate is going to be the y moment over m. The y moment is the integral from a to b of, let's see, what was the y moment? I can't remember. The y moment is rho f of x. Rho f of x dx. This is going to be divided by 16/3. So like what I said last time, dividing by 16/3 is the same thing as multiplying by 3/16. And now we can plug in what we're dealing with here. We're going to integrate from 0 to 4. We can set the rho equal to 1. The f of x equals root x. And then we have multiplied by x dx. Okay, so this is not going to be that hard to integrate. Let's do it down here. So we're going to get 3/16 of the integral 0 to 4. X is x to the half. X is x to the first. So we're going to be integrating x to the 3/2. Okay, and then we can calculate the antiderivative. Okay, so if f of x is, so if our function is x to the 3/2, what's our antiderivative going to be? Well, it's going to be x to the 5/2 times 2/5. Cool. Okay, so we have to calculate f of 4, so you're going to get 2/5, 4 to the 5 halves. F of 0 is not going to give you anything. So what is that? What is 4 to the 5th? I'm opening up a thing. Okay, so I'm opening up a calculator. What is 4 to the 5th? 4 to the 5th is... It's calculating 1024. And then what's the square root of 1024? 32. So you get 2/5 of 32, which is 64/5. Okay, so you're gonna get 3/16 times 64/5. 64 divided by 16 is 4. 4 times 3 is 12, so you're going to get 12/5. And 12/5 is 2.4. So there's our y coordinate. Or sorry, x coordinate, my bad. We were calculating our x coordinate. So if we scroll back up, so where's our center of mass? Actually, I made a pretty good guess. X equals 2.4 is like right here approximately. So apparently to balance this thing, you would put a point right here at 2.4 comma, what was the other number that we got? 0.75. So it's like to the right quite a bit and then not too low. Or sort of low. Okay, so if you were to like basically cut this as a piece of wood, that's where you'd want to balance everything. Okay. Boom. What time is it? Oh, that took a while. These questions, like, they go, some of them take a long time. Like readjust the stuff on my desk. There we go. Okay. I'm gonna move what topic we're talking about now. Unless there are questions, so I'm gonna pause for a moment and see if there are. Is P, the row? Yeah, the row will always be given. If it's not given to you, just use row equals 1. It's a good question, actually. Any other questions? Okay. Cool. How many days? Questions about the what's it called? You will find out. Let's say, yes. You will find out. Questions about the material. I understand. Okay, so out of curiosity, actually no, I just want to ask. Like, you'll find out. I'll just say that. But why does that occur to your mind first? Let's talk about that. Why do we want to ask about that right now, other than the fact that I guess you're worried about it? I guess I should interpret your question as like a possible anxiety. My job is not to make you like get to fail. Okay. Still lost on the X bar and Y bar stuff. Like, what about it? Like, so like X bar and Y bar are the X coordinates of the center of mass. So I'm assuming that's not your question. It's probably deeper than that. So like, where do we get lost? Like, we have these formulas for them. Are you lost about where the formulas came from? Like, are we wondering, like, where these integrals? There's a lot to it, I will say that. And, like, usually to understand this, you have to what I highly recommend you do is you sit down and you go and you draw through this example that I put here. So, like, draw the lamina, draw the little rectangles that do the approximation, and then go through one of the rectangles here and try to find the center of mass for that rectangle. And you will realize that the x moment and the y moment give you these formulas. Okay, now once you have a formula for one of the rectangles, you can sum that formula, right? And then take the limit and you get the integral. So once you understand how the x moment and the y moment for that rectangle give you these two things, which are, like, have the little, like, dashed boxes around them, that will really help with that. Does that sort of make sense, though, what my advice is? Like, if you're looking at this and you're like, man, where the F is this coming from? That's what you need to do. Like, draw the thing yourself on the side, like, and then puzzle through, like, sort of, I talked through it already a bit, but, like, I understand that you're probably not going to get that on, like, the first run, which is why this stuff is sort of difficult, like, understanding where it comes from. Does that sort of help out? Is that, because I don't think just saying it again will help. Yeah. Like, my best advice, because I remember, like, taking this class too and being like, holy shit, like, where the hell did that come from? I'm never going to remember that. You just have to sort of sit there and, like, puzzle it through. Which is why I did all these examples above, Burrito, stop. I did all these examples above here about, like, how do you get the moments if you have, like, some point masses. It's the same knowledge, it's just now it's being applied to this rectangle over here. Okay, so if you use the earlier stuff to, like, inform what you're doing, that will help a lot. Okay. Other things that we want to ask. So mx and my are the y moment and x moment, yes. Y bar and x bar is the y, yeah. Okay, so I guess that's actually probably an issue here. So let me, like, draw a picture here to explain. Okay, so you have your, let's just draw this shape. So, like, right here, that's going to be your center of mass. X bar is the x value of the center of mass. Y bar is the y value of the center of mass. Now, what are the formulas for that? Well, the formula for x bar is equal to the y moment divided by the mass, and y bar is equal to the x moment divided by the mass. Now you might be wondering, like, why the hell is that? It threw me off for a second too, so let me explain, like, why that's the case. So you draw a little rectangle. And here's, like, the midpoint of that rectangle at x star. Okay, and this rectangle is on the x-axis, or there's like a y-axis and an x-axis. There you go. Okay, now looking at this thing, does everyone agree that its center of mass is, like, right here? Right at that red dot? Because if it's a rectangle with constant density, you know that the x point for the center of mass will be in the middle, and then so will the y point, right? So this point right here is x star comma f of x star over 2. Okay? Which means you have a distance from the y-axis and a distance from the x-axis. And this is the weird thing. If we're talking about the x moment, we're talking about, like, we're gonna, how do I say this? Let me make sure I have this lined up right, because I don't want to screw it up. Let me quickly look at this before I say anything, because I don't want to say the wrong thing. Ah, there we go. So, the x moment is about the distance from the x-axis. Now, what variable helps you measure distance from the x-axis? Like, if you look at that point, would you use the x variable or the y variable to measure the distance to the x-axis? Honest question. If you have that little red point right here, burrito, stop. Okay, if you got that little point right there, how are you going to measure the distance to the x-axis? You're not going to use x values, you're going to use y values. Which is why, for the x measure, you get an mi times a y value. So that's going to be your mass times your y value is that f of x star over 2. So your x measure will ultimately determine the y value of your center of gravity. Now, if you're talking about the y moment is the distance to the y-axis. And what variable do you use to measure distance to the y-axis? The x variable, which is why the y moment is going to be used to calculate the x value of the center of mass. So that is like a super confusing thing, yes? Because it's like the complete opposite of what you would want, right? So you have to remember that the x moment tells you about the distance from a point to the x-axis, which will be a y value. And then vice versa for the other one. Person who asked me that question, does that sort of clarify that a little? Okay, good. I mean, I hope it does. Because I know that when I remember, like, even when I was like preparing for today, I was like looking at it and I was like, oh man, I remember this. Like, it's this annoying thing where it's like completely counterintuitive, where it's like the opposite of what you would want it to be. Okay. Can everyone hear the kids screaming outside? Or is it just me? Like, does it come through on my microphone? Oh my god, okay, yeah. I like hear them like screaming outside in the courtyard. Which is like cool, they're having fun. But it like throws me off. Oh yeah, okay, cool. It just like, every time I hear them, I like, part of me, like, it's like, I have like auditory sensory issues. So like when I hear shit in the background, it like throws me off. Does it make sense? So like as the kids scream, like my mind like jumps over there and then I'm like, ah! And then I have to like reel myself back in. It's a struggle. Okay. I guess this is one of the non-joys of, you know, working from home. You get to hear little kids screaming all day long. But it is what it is. Hey, we have a couple minutes left. There's one more topic I want to introduce. Okay, and this is something called hyperbolic functions. These are actually really cool. And they're really useful. Like in engineering. Okay. So, let's talk about what hyperbolic functions are. So let's just give you the names of these things first. there are three hyperbolic functions. Singe, cosh, and tange. So you can probably guess what the H stands for. The H stands for hyperbolic. So this is called the hyperbolic sine. This one is the hyperbolic cosine. This one is the hyperbolic tangent. Perhaps you've seen them on the calculator. They like show up all the time. Okay. So, let me tell you about this one, the hyperbolic cosine. It shows up in physics and engineering a lot. So let's say that you have a point like right here and another point right here, and then you hang a string between them. Does anyone know what shape this is called when you just like hang a string from 2 points and just let it rest? There's like a special name for it. Have we heard it ever? No, not a parabola. It looks a lot like a parabola. It starts with a C. Not a half circle. I'm going to put 3 letters, and if no one gets it, then I'm just going to tell you. I'm just curious to see if anyone's ever heard of it before. Okay. It's called a catenary. And it's basically an arch. Has everyone heard of the St. Louis Arch? Right, it looks sort of like this. Arches are the upside down shape of catenaries. So a catenary is the shape that you would get if you just let everything hang naturally. It's why they actually provide a lot of support. The St. Louis Arch, like it's a super solid structure because it's the opposite of something just hanging at rest. Okay, so interesting fact, the shape that these catenaries take, it's the hyperbolic cosine. So it shows up all over in the world because a lot of the times, like when you look at structures or when you look at here's another interesting thing. Has anyone ever been to one of those like bubble shows where like they have like a hoop or they have like some weird shape and then they dunk it in the soap water and then you see the bubbles get made on them? Does everyone know what I'm talking about? Like the bubble shows? Like you get like a hula hoop or some weird thing and you dunk it and then you can see the film that it makes. The shape that those things make are actually related to this. Yeah, exactly. I mean, one of the reasons they push those is because it's like a science demonstration, but no one ever like actually talks about the science and physics behind it. So if you look at like, these are called surfaces of least area. Burrito. No. He's like growling at the kids. Okay, so if you look at these things, these surfaces of least area that you get when you make like bubbles and whatnot, they actually are super related to these catenaries. Which is why like we're interested in studying them. So like hopefully this gives you an idea of like why do we give a shit about this? It's because it like shows up all over the place, like in like bubble surfaces, like things that are hanging, right? Like physics and engineering in particular like cares about that sort of stuff, right? Okay. So let me just give you the definition of these. So like what is the formula for your hyperbolic sine? The formula for the hyperbolic sine is e to the x minus e to the minus x over 2. Now, if these are anything like regular sine, what should the derivative of hyperbolic sine be equal to? Yeah. Okay, and interesting fact, it is, the hyperbolic cosine is e to the x plus e to the minus x over 2. And we could take a moment to like go through and calculate it and you would see that this is exactly what happens. So like if you take the derivative of e to the x minus e to the x over 2, well, you can factor out the 2. And then you're going to take the derivative of the difference of these two. What's the derivative of e to the x? Yeah, boom. And then you get minus. Now, what's the derivative of e to the minus x? So you have to use the chain rule. You get you get the derivative of minus x times e to the minus x, right? And if you go and you calculate this, yeah, you get e to the x. The derivative of the derivative of negative x is minus 1. And then what happens to these two minuses? They cancel and give you plus. And then notice that this is exactly that one over there. So it's like sort of crazy. Like it follows a lot of the same properties that sine and cosine follow. And it has a lot of practical connections. Now here's sort of the weird thing. Do you see how we call this sine and cosine? But do you actually see any sines and cosines over here? No. It's hyperbolic sine and hyperbolic cosine are written in terms of the exponential. Has anyone ever heard of the Euler formula? Do you remember that from pre-calc? Did anyone learn the Euler formula in pre-calc? It actually tells you that there's a relationship between the exponential and cosine, which is where this relationship comes from. So anyways, I think we're done. Yeah, Euler had like almost all the formulas. The guy was like a super genius. We're going to talk about this more next class. I'm going to be releasing the final later today in a little bit. You will have like until next week to finish it next Friday. Yeah. Oh, yeah. Let me open a thing to do that right now. What is tripping you out, Manshal? Okay, I'm opening it right now to open them. Great scope.